Hello YouTube. So today I will begin a series that covers differential equations, and it's not like some random video that I posted before where I just cover a random topic from a random course. I'm going to be formally covering all the topics in differential equation, or at least most of them, that you'll find in a college class. So in this video we won't be covering any specific topics. I'll just be explaining what differential equations are and their necessity. So to start off with, what are they? Well, simple. It's just equations with derivatives in them. Okay, that wasn't it. So what that means is, or I'll just give an example. So let's say you have function y, which is a function of x, so y equals f of x. So you could say, for example, the first derivative of y with respect to x plus 8x equals, I don't know, y. That's a differential equation because of this term here. It has the first derivative of y with respect to x. There's a derivative in there, therefore it's a differential equation. Another example of a differential equation, I don't know, say we have y as a function of t. So we have the second derivative of y with respect to t times 9 plus, I don't know, 8 dy dt plus y squared equals 8. This is also a differential equation because these two terms here, they have derivatives of y with respect to t. They're derivatives, so they're differential equations. Okay, now let's cover why we need these and how they actually appear in the natural world. Okay, so oftentimes differential equations are used when it's much easier to model processes through their derivatives rather than their actual function. So I'll just give you an example. So let's say we have a ball that's in free fall and it experiences a gravitational force of Fg and an air resistance force of Fa. So we know that the net force is equal to ma. That's what you learned in a high school physics class. F equals ma, Newton's second law. That's equal to Fa minus Fg. Net force, just the forces trying to balance each other out, although they don't fully balance each other out. So we know that Fg is equal to m times g, and we know m is mass, so just write m is mass. G, gravity's acceleration, so it's a constant. B is air resistance constant. And we know Fa is equal to bv, where v is the velocity of the, I'll just say ball, going downwards, and b is the air resistance constant that depends on the medium it's traveling through, the shape, size, mass, everything about the ball. So we can rewrite this as ma equals bv minus mg. Okay, well, we know that, let's say we can define position as x, so x is position, and obviously position is also a function of t. So we know that the first derivative of position is velocity, and the second derivative of position with respect to time is acceleration. That's just basic physics, which you guys probably already learned. So we can rewrite this instead of ma equals bv minus g as m second derivative of x with respect to t equals b dx dt minus mg. So Finding the solution of this equation is rather complicated, but as you can see, it's much easier to write this equation of motion in terms of x's derivatives rather than x itself. We'll learn how to solve for x in later videos, but for now, this is what you're going to get. This may allow you to understand why it's so much easier to have differential equations than actually solving it. Okay, now let me cover one more example before I end this video. Sorry, cleaning this is a bit tedious. Okay, so now let's say we have a pendulum. So it's a string with a mass attached to it, and let's say that it oscillates with an angle theta, and this thing has a mass m. So okay, it oscillates at an angle theta from the vertical, and it just goes back and forth between this position. Sorry, that wasn't a very good drawing, but you understand what I'm trying to say. So this can be modeled, or the motion of this can be modeled through this differential equation. So second derivative of theta with respect to t equals the negative g over L. So L is the length of the pendulum. Length of pendulum. So if this is a string and this mass is dangling, the length of the string is L. So equals negative g over L, g is gravitational constant, times sine theta. So finding a closed form solution is impossible. You may be able to express this in terms of Taylor series, but basically this is impossible to find a closed form solution of. You'll just end up with some complicated function that you have to invent to solve this equation, also known as the elliptical integral. If you're interested, you can search that up. The solution of this pendulum equation is called elliptical integral. So as you can see, it's pretty much impossible to express this in terms of theta. So that's why differential equations come in handy. You can express the motion of this pendulum ball without having to have theta itself. And you know what a lot of engineering books, or what pretty much all textbooks and classes have, is they'll have this approximation where they'll set sine of theta approximately equal to theta. And the reason for this is because the Taylor series of sine theta is equal to theta plus minus 1/3. Okay, I'm back. 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the 5th, and so on. But if you have very small angles, so when theta is really small, these terms become insignificant, so negligible. So then that's how this reduces to this. But when theta is not negligible, when theta is big, like 30 degrees, 60 degrees, then this differential equation you kind of have to deal with, rather than being able to just reduce it to something like this, something simpler like this. You won't be able to do this when theta is big. Okay, anyways, thank you for watching this video. I'll see you in the next video.